Lab Guy here. This will be the final video on the Craig 6104 restoration project. As you all know, that project went up in smoke and was costing me far too much time for too little progress. So I've called it. Today we're going to review all of the information I obtained from this camera during the process of the attempted restoration. It can probably still be restored, but the number of episodes involved and the amount of work without the service manual at hand is becoming unrealistically excessive. So, as I said, I've called it. So today we're going to go through the features of the camera, the information that I discovered and extracted personally in the absence of the service manual. I had to extract the schematics manually myself. I'll let you know right now before we go into that I didn't completely schematify the camera. It's 95% traced out. It was more than enough to be able to work on the camera. And so I accidentally put in a power supply capacitor backwards. It happens. It happens. And there you are. So there are so many projects in my queue ahead that are just as exciting and just as significant that I can no longer justify this project. It's over. So without further ado, let's get into reviewing the Craig 6104 video camera. So moving right along, let's start with slide number 1. This is the brochure front page for the Craig 6104 video camera. This camera came out in approximately 1965. I don't know the exact release date, but we'll say 65, and we're within plus or minus 1 year on its introduction. The Vidicon camera with reflex lens viewfinder. What that means is that there's a little peep scope that looks down through a prism through the lens. Solid state construction, automatic light compensation through the lens viewfinder, as mentioned. It's compact. For 1965, this is a very small camera. It's lightweight. It accepts C-mount and 16mm motion picture lenses. Classic marketing line there. C-mount and 16mm mount are the same mount. Very well, let's flip this thing over and look at the back side. On the back of the brochure we can see the complete ensemble with the tape recorder, a monitor, and a sweet roll-around storage cart used in schools, hospitals, other institutional settings. There's a model diagram of the camera showing the location of various controls and switches and jacks. So I'll read the specifications for those who are looking at this on phones and probably can't read this without magnifying, so let me run down the list for you. Specifications: horizontal frequency 15,750 Hertz. That's the US horizontal scanning frequency. Vertical frequency 50 or 60 Hertz locked to line. That would depend on the particular country the camera was sold in, but the vertical scan is indeed locked to the power line. Interlace is random. The power line frequency and the horizontal oscillator are separate. They're free running relative to each other, so there is no interlace. The interlace is random. Horizontal resolution more than 400 lines. Now this specification on cameras can be confusing to some people. in the sense that they confuse resolution lines with scan lines. These are two different things. There are, in the US scanning system, in EIA, there are 525 total scan lines in a frame of RS 170, what is mistakenly sometimes called NTSC, black and white video. The frame rate is 30 hertz. The field rate is 60 hertz. And the number of scan lines that are active is between 480 and 488, depending on the particular sync generator. Horizontal resolution lines are this. Imagine your camera is pointed at a white picket fence with a black background, and you are zoomed in close enough so that you see 10 pickets. So there are 10 white stripes and 10 black stripes. If that was the maximum resolution the camera can display of vertical black and white pairs, that would be 10 lines of horizontal resolution. So we start pulling the camera backwards and the pickets start getting narrower. So there's more and more picket and space until you reach 400 lines. What this means is 200 line pairs, a white line and a black line. In this case, this camera can discern up to 400 pairs of lines, a black, a white, a black, a white. Now, as the camera pulls farther away, these will begin to blend together and form a gray field of 50%, because we're assuming 100% white for the white stripe, 100% black for the black stripe. So you end up with a gray. So moving on, they claim a signal-to-noise ratio of more than 40 dB. Well, that's very good. That's a good, clear picture with no snow in it. Standard illumination, 500 lux, and a minimum of 100 lux. 100 lux is equivalent to about two 100-watt light bulbs, one on each side of the camera, in a typical living room, let's say, and that will produce a picture. Not a very good picture, a low contrast image, but it will make a usable picture. They're saying that 500 lux, 5 times that much light, is way better, that you'll get a full black to white range contrasty picture. Electrical focus, fully stabilized to compensate for temperature and line voltage. So it has a regulated current to the focus coil around the tube. Power is 117 volts AC, 60-50 hertz, and the camera draws about 8 watts of power. The Vidicon tube is a 2/3 inch type 20 PE11, as we've established throughout the series. Solid state circuitry, 31 transistors and 15 diodes. Operating temperature -5 degrees C to 45 degrees C. The controls: external, power switch, lens focus, eyepiece focus. Internal, through the rear plate, beam, electrical focus. Under the cover, horizontal frequency, width, height, and vertical linearity. And the guarantee is standard 90-day guarantee. So that's the Craig 6104 in a nutshell. Let's move on to the schematics that I captured. Looking at the power supply first. In the upper left corner, we have the power transformer, which had 3 output windings. Its input is a 120 volt winding with a power switch and a pilot light. The first winding is the 6.3 volt winding for the heater in the Vidicon tube. This is a standard tube heater winding. The next winding is the low voltage winding used to generate the voltages needed by the transistor circuitry. It is a 40 volt center tapped winding that is 20 volts and 20 volts on each side of the center tap. We'll get into that in a minute. Then the high voltage winding, which has a 360 volt tap at the top and lower down a 100 volt AC tap, which is used for the negative bias, which controls the grid in the tube. Looking at the rectifier board circuitry, at the top, the first input is the 100 volts AC, which comes in to a diode, which is positioned as a negative voltage rectifier. It's filtered by two 5 microfarad capacitors and a 45K series resistor. It's fed into a potentiometer, which I did not record the value of, but gives us a control voltage range probably in the range of 0 to 110 volts DC negative, which goes to G1 of the Vidicon tube. When this control is more than about 30 volts negative, the beam in the tube will be cut off. It operates somewhere between minus 20 and minus 30 volts. The next input on this board is the 360 volts AC. They've put two diodes in series like I did in the NBTV televisor project because the single diode couldn't handle the voltage. These are probably 250 volt rated diodes. So they've coupled up a pair of them to increase their voltage handling capability. Again, we have a capacitor resistor pi filter, two 5 microfarad 500 volt capacitors. The second one was the one that I installed backwards and burned up this resistor. The value I've written there is my best guess after it was burned up. It burned all the stripes off of it. I measured it. It measured 8K after it was burned up, so I have zero confidence in that resistor. And moving on, you notice that the output of that filter goes to 4 voltage dividers. The farthest out one is the 680K 4.7 meg divider, goes to pin 2 of the Vidicon tube, which is G2, the focus electrode. They're putting a fixed voltage on the electrostatic focus electrode in this tube. Pin 2 on the Vidicon tube. The next voltage divider to the left, 1.5 meg 330K, that produces a voltage that's sent over to the ALC amplifier on the video board. This is providing the target voltage for the Vidicon tube. We'll talk about the ALC circuit when we get to the video board. The next voltage divider is a 470K 1 meg, approximately a 2/3 divider here, which provides voltage to G3, which is the accelerator electrode in the tube, and that is on pin 7 of the Vidicon tube. The next voltage divider establishes a voltage and current that went to the focus coil, the focus coil around the Vidicon tube. There is more circuitry associated with it. This goes to the video board into the 9-pin connector on pin 8 and is associated with the current in the focus coil. The next board that we'll look at is called the scan centering board. One of the 20 volt AC taps was sent to this board from the power transformer, was converted into a negative 22 volts by a rectifier diode, and provided to a current source composed of a transistor and some resistors right here, and produced a current flow in two 10K pots. These 10K pots no doubt go to one side of the deflection yoke, and they provided a variable DC current between plus 12 volts and minus 8 volts, which was used to adjust the vertical position of the scan and the horizontal position of the scan. Most of these cheap cameras don't have centering controls. There are a couple of ring magnets around the base of the yoke on the tube, which usually is used for that. In this case, because of the optical viewfinder, they had to be able to move the scanning raster around on the tube to match what was visible in the optical viewfinder. They would point the camera at a calibrated chart and peep through the viewfinder and align the camera to that, and then align the vertical and horizontal centering and the vertical size to match what was seen in the viewfinder on the video monitor. And that completes the power supply page. Moving on to the deflection board, on the upper left we can see the horizontal scan circuit. It's composed of an LC oscillator running at 15,750 cycles per second, followed by Q2, which is a buffer transistor driving Q3, the horizontal output transistor. This was coupled to the deflection yoke and those centering voltages I mentioned before. It's a very straightforward, simple circuit. If you want to see a circuit similar to this, look at my project called The Chief, my Indian head test pattern generator, where I go into much more detail about designing this kind of a circuit. A tap is made from the Q2 video buffer and fed over to two diodes forming an OR gate, which sums a pulse from that output with the pulse from the vertical circuit to produce the composite sync output. We'll get into that in a minute on the video board. Down below on the bottom half of the schematic is the vertical deflection. You'll see that on the far left, the first thing coming in is 60 Hertz from the 6.3 volt winding in the power transformer. It's coupled into a clipping circuit and inverted, fed across a capacitor, fed to a one-shot circuit, which is set up to produce a square wave of about I'm going to guess about a 20% duty cycle, maybe 10% duty cycle. It's turned into a shortened pulse, which is fed over to another OR gate circuit that would be Q4, which also gets a pulse from the horizontal oscillator and a pulse from this one shot, this multi-vibrator, and produces the blanking, composite blanking of both horizontal and vertical blanking pulse that is also sent over to the video board. Passing on from there, there's another video inverting buffer, which is used to send the vertical pulse to the comp sync OR gate, and the drive pulse into the three transistors that form the vertical scanning circuit. I'm not going to go into a lot of detail of how it works because, to be honest with you, I haven't analyzed it to any depth, but it has a ramp generating circuit in there with a constant current source and a switching transistor that switches and shorts out or charges up 220 microfarad capacitor as the primary vertical scan generating capacitor. Q5 and Q6. Q5 is a current source and Q6 is an amplifier follower. The 220 microfarad capacitor on the output coupled the output signal to the vertical deflection coil, and probably the reason I don't have anything connected to vertical deflection coil 2, shown here as a symbolic flag, is because that is taken up at the vertical centering control on that vertical centering board I mentioned. That completes the deflection board. Moving on to the video board. The first thing I want to look at is the power supply regulator on the left on the bottom. And what we're looking at is 2 of the 3 transistors that make up this circuit. The third transistor was a power transistor on a heat sink off board. It forms a classic negative feedback circuit to produce the regulated 12 volts. The transistor Q12 is coupled with the off-board transistor to form a Darlington transistor, which is just a very high gain transistor. Q11 here on the bottom is configured as a inverting amplifier. It picks up the error voltage from the voltage divider, voltage set pot, and subtracts it. If the 12 volts gets too high, it turns it down. If it gets too low, it turns it up. A very straightforward voltage regulator. The next circuit to the right of that is set up as the focus coil current regulator. Previously on the power supply board, we had the current circuit sending current to this circuit on this board, which completes the current regulator. And as you see on the right side, the focus coil is getting that focus voltage coming in on J1 pin 2, then is regulated through a current regulator, the most right-hand transistor, and is sent as a current to the focus coil, which returns back in here and goes to ground through the 68 ohm resistor. And the emitter of Q16 is set up as an input in this case to create a negative feedback circuit between the base and the emitter to control the current in the final transistor. It works similar to the voltage regulator, except in this case we're regulating current. Let's move on to the video amplifier. On the extreme left, we have the Vidicon target coming in. For the target to work, it needs a DC voltage. Remember, we had the ALC, which is automatic level control, coming from the power supply circuit. It's a voltage higher than the 12 volts. It's controlled by Q5 as a shunt voltage regulator. It's coupled through two 22 meg resistors, extremely high impedance, and 2 capacitors, which act as noise filters, because the Vidicon target input is extremely high gain and sensitive to noise. So we have this intense low pass filter that removes all the noise on the ALC power line. This provides a DC bias to the Vidicon target. We'll get back to the rest of the ALC circuit in a moment. So the Vidicon signal comes in and is AC coupled into Q1, which is a high gain inverting amplifier. You'll notice that the upper leg has a filter made of a 12K resistor and a 10 microfarad capacitor. This guarantees that the DC voltage coming to this collector circuit is as clean as possible, as quiet as possible, because this is a very high gain amplifier. And then it goes to the next transistor, Q2, which is set up as a high gain amplifier. Its output goes out through the 10 microfarad capacitor on the collector. But meanwhile, down on the emitter, it is configured also as an emitter follower circuit with some heavy filtering on that circuit, which is adjusting the frequency roll-off response that occurs with this high impedance input circuit from the Vidicon target, and is forming a negative feedback loop, closing the gain on this amplifier. The 3 resistors in the emitter and the 2 capacitors on that network form the compensating network in the feedback to make up for the frequency roll-off. So as the frequency goes up, the gain goes up so that it flattens the frequency response of the video. Remember the picket fence? This is what gives them their claimed 8 megahertz of bandwidth. Moving on through the 10 microfarad capacitor, we come to another gain stage buffer, which is actually running as an inverter. It comes through this inverter and comes down, and we'll go first through the ALC circuit. It goes into a gain stage inverter made of a PNP transistor Q7, where the signal is inverted and amplified and fed into an emitter follower circuit made up of Q6 and is coupled over a capacitor into a voltage doubler circuit. 2 diodes, that coupling capacitor, and the output capacitor, the two 1.5 microfarad caps, which is then coupled through the 1.5K into the ALC control transistor. This rectified voltage represents the average voltage of the image from the Vidicon tube, from the video information. And if the video is bright and the signal is high, this will produce a high bias voltage onto this transistor, and it will turn down the voltage on the ALC. If the signal is low, this circuit will put out a lower voltage, which will relax transistor Q5, and the ALC voltage will rise, and increasing the target voltage and creating a negative feedback loop there that keeps the output signal from the Vidicon tube relatively constant. Going back up to the output of the first 3 stages of video amp, we go through another gain stage, which is comprised of Q4 and Q8, configured in another negative feedback arrangement. And Q8 is running as both an emitter follower, I believe. No, it is not. It's running as an inverting amplifier. The 3.3K resistor is providing negative feedback to the emitter of Q4 again to control the gain of this stage. And when you do that, you open up the bandwidth of these transistors. There would be a roll-off in bandwidth, and this circuit closes that and kind of flattens the bandwidth of the pair. Now, the output of Q8 is AC coupled and is connected to Q9, which is driven with the clamp pulse. That came from the scan board. They didn't call it clamp over there, but it was the sync output, or the what they called blanking. They called it blanking. And here it was called clamp on this board. They changed the name of the signal as it crossed over, but it's the blanking from one of those 2 diode OR gates I showed you. So it comes in and switches Q9 off and on. Do I have 2 Q9s? No. Okay, Q9 switches off and on. When it's on, it connects the 104K 0.1 microfarad capacitor to ground and shorts it out, which sets the blanking level of the video to 0 volts. That is a 0 volt clamp for the video. DC restoration. The next stage is a simple emitter follower and summing circuit on its emitter, where the sync pulse comes in on the yellow wire, goes through Q question mark, and it controls the emitter voltage here. It switches it to 0 or relaxes it and lets the 12 volts pull it up, which adds a sync pulse to the non-composite video on the base. And at the output of transistor Q18, we now have video with sync pulses added, clamped video with sync pulses added. It's again goes through an emitter follower as a buffer amplifier, and drives the output transistor, which is configured as another emitter follower, and with a low impedance output coming off of the emitter to the video output jack. And that is the complete circuitry as I have mapped it in the Craig 6104 camera. Now let's look at the Vidicon tube and see what the difference between the 20PE11 and the Vidicon 8844 was. I had to change the wiring very minutely. First, let's look at the 8844 to look at a properly mature Vidicon. The 20PE11 was one stage in development earlier than this. We've come back to that. Looking at the diagram on the right is the pinout of the 8844. Pin 1 is the cathode. The heater is on pins 3 and 4. The heater heats the cathode to make it emit electrons. The first grid, G1, following the cathode, is the control grid, which is what the beam control hooks to. That is operated at a negative bias between -20 and -30 volts to control the intensity of the electron beam. G2 is the next grid in line, and it is a focusing grid and works in conjunction with G3 to form and G1 to form an electrostatic potential which focuses the beam along with the magnetic field of the focusing coil. G2 is operated at a fixed voltage. G3 is operated at a voltage higher than that, and it is the accelerator electrode to accelerate the beam to the target, labeled T in this case. Target is taken off of a metal ring at the front of the tube. That is the signal that goes into the video amplifier. The image is focused onto the target. The beam scans the target, and based on the amount of voltage present at each location on the target as the beam sweeps, or more precisely the amount of light, its resistance varies, its conductivity varies, and produces a varying output signal, very minute output signal. G4 is the booger bear in all of this. With the 20PE11, G4 is bonded to the end of G3 inside the tube. They're not different. And G3 was connected electrically to both pins 2 and pin 7. Okay? Looking at this one, you can see that G3 is on pin 7 and G4, which is the screen electrode, which its function is to take that electron beam. If you look at the picture on the left, you see that the electron beam is bent at a point in the middle of the tube and arrives at the front of the tube at an angle. We don't want that. We want it to arrive parallel to the face of the tube. The mesh, as it's called on this diagram, is G4, and its job is to straighten that electron beam so that it arrives perpendicular to the target electrode so that it produces a round sampling spot, not an oval. If this wasn't corrected for, the electron beam would only produce a round, perfectly round spot at the center of the target. So this is a, I want to say parallax correction methodology. That's not necessarily the right word, but you get the idea. When the beam is bent like that, it'll make an oval spot, which reduces resolution. The screen will straighten that beam to arrive in a straight line all over the target. And it is kept at about the same voltage as G3. So in the case of the 20PE11, they bonded it directly to the tube. In the 8844, it's a separate electrode so that in theory you could make that an adjustable voltage and make the corner focus even better by trimming it slightly in voltage. It's not necessary. I discovered that this electrode could be directly tied to G3 by looking at the schematic of the cartridge vision camera, where that is exactly what they did. I knew the cartridge vision camera used an 8844, and so when I looked in there, lo and behold, pin 2 and pin 7 of the Vidicon tube were tied together. They had tied G4, the mesh electrode, the screen grid, they had tied it directly to G3, the accelerator electrode. So in the Craig camera, pin 7 was a no connect, so I simply wired a wire across from pin 2 to pin 7, and that's when the 8844 tube in the Craig camera started making pictures. So that was how I corrected for the Vidicon tube situation where I could not find a single good working 20PE11. I obtained 5 more 20PE11 tubes. All 5 of them had gone gassy. They all had air inside, including the tube that was in the camera. So this forced me to switch to the 8844. And that's that story. So we have now covered everything I discovered about the Craig 6104 video camera in this project. This completes the review of the Craig 6104 camera. Thank you for watching to this point if you've stuck it out. I'd like to welcome all of the new subscribers. We passed 2,800. As of this moment, I have 2,803 subscribers according to the YouTube control panel. And I thank you all for signing up. Hopefully future programs won't be as unsatisfying as this one was. So welcome, thank you. Greetings to all of my current subscribers. You guys rock. Thank you for watching my videos. Thank you for whatever it is you're supposed to do. I keep forgetting what you're supposed to do, and I'm so sick and tired of the cliche of that. I've noticed in a few videos that I get a thumbs down now and then. You know what? That's perfectly fine. If you're going to leave a thumbs down, please leave a comment and let us know why so we can fix it. And I'll do my best to improve on that, whatever has dissatisfied you. If you're having a bad day, I think there's better videos you could go thumbs down if that's what you need. I mean, everyone needs to kick the dog once in a while, right? Figuratively speaking. So, there you go. Thank you for watching the Craig 6104 Resurrection series. And it's Easter. So, until next time, Lab Guy out.